Welcome to Regular Expressions, Regexes in Python. My name is Chris, and I will be your guide. In this course, you will learn what a regular expression is, when to use it and why, how to use matching characters and ranges of characters in your regular expressions, how to control the placement of a match, how to group and repeat patterns in a match, using the Python regular expression module to apply regular expressions in your code, and how to modify the behavior of a regex using the flag parameters. A quick note, the samples in this course were tested using Python 3.8.2. For the most part, regexes have been there since almost the beginning of Python, and there haven't been that many changes. There are some subtle differences in how the re.sub method works in Python 3.7 when you are using zero-length matches, but most people don't run into this. And the other big change between Python 2 and Python 3 is, like everything else in Python 3, the regexes default to Unicode. Besides that, anything you see should work fairly consistently across any version. Regular expressions are a language in their own right, so they're really sort of a language inside of Python. The short form is regex. You'll hear me using that frequently. And what is it? It's a sequence of characters that defines typically a search pattern. This is matching some text using the pattern, and is commonly used inside of a lot of applications for find and replace. The concepts behind regexes were kicking around in the 1950s and were first formalized in a paper by Stephen Cole Kleene. There are a number of different syntaxes of regexes. The two most common are the POSIX standard and what's often referred to as Perl syntax, or Perl-compatible regular expressions. So where would you use a regex? Their primary purpose is text matching. This might mean verifying the user's input complies to something. For example, whether or not a phone number input by the user matches the pattern a phone number is expected in your locale. They're often used in applications for search and replace. Find this chunk of text, replace it with that chunk of text. If you're familiar with the split and replace methods inside of the Python string library, there are regular expression versions of these that are far more powerful, allowing you to define complicated patterns for splitting on and complicated patterns for matching and replacing. One of the more powerful parts of a regular expression is you are able to define the expression in such a way that you can parse out multiple parts of a string, identifying different components as it goes along. This allows you to do complicated matching mechanisms in one pass. You can find regexes almost everywhere in computer software. There are a variety of Unix utilities that use a base version of regexes, including sed, awk, and grep. And many word processors and text editors used for coding use regexes to enhance the capabilities of search and replace within the software. The POSIX standard for regexes has two parts: the basic regular expression mechanism and the extended regular expression mechanism. If you are using grep, by default, it uses the basic regular expression definition. Some versions of grep have a flag that allow you to use the extended regular expression definition. There's also a program out there called egrep that uses this by default. Most major programming languages support, through some library mechanism, some variation on regexes. Perl, Java, JavaScript, Julia, Python, Ruby, the list goes on. Many languages, including Python, use the PCRE with some minor differences. In the next lesson, I'll introduce you to your first regular expression, with character matching and ranges of characters. In the previous lesson, I gave you a quick overview of what regular expressions are and how to use them. In this lesson, I'll show you your first regular expression, showing you how to do plain character matching. Regexes can range in complexity. The simplest concept is just a plain string match. This regular expression looks for the 5 letters THING inside of the text it's being applied to. It'll match anywhere where the word thing is. To be strictly correct, I shouldn't use the word word. THING will match thing on the end of something, as well as thing on its own. There's nothing in this plain text match that talks about the spacing around it, so it's specifically only looking for those 5 letters. On the other end of the complexity spectrum, there's how to match an email address header inside of RFC 822. The code I'm about to show you comes out of a Perl regular expression for a library that looks for these headers. It's a little insane. Don't worry, no human being actually looks at this. It was created by comprising several smaller regular expressions that are easier to read together. Later on, I'll show you where this came from. But for now, I'll get you started with simpler matching. As I mentioned in the overview, regexes are a language to themselves. In order to understand how to use them in Python, you'll need to understand both regexes and how Python uses regexes. So to get started, I'll be teaching you only regexes. Now I'll show you the Python variant of them, but I won't be showing you any Python code for the first few lessons. I'll just be showing you the regexes. Later on, I'll show you how to put those inside of your Python code and how to use the regular expression module. First up, I'll show you some plain text matching, and then after that, I'll introduce you to character classes, a way of choosing from a range of characters. To introduce you to the language of regular expressions, I'm going to be using an online tool called Pythex. There are several different websites out there that help you build and debug regular expressions. This is just one of them. In the further reading section, I'll show you a few more. The tool is comprised of three basic parts. The first line is where the actual regular expression is. Then there's a text area of the string that you are testing the regular expression against. And then down at the bottom, there's an area showing you the matching. Throughout these lessons, I'm going to be using the same chunk of text, so you'll be very familiar with it by the time you're done. The text is an email message from Wile E. Coyote to the Acme Corporation complaining about their products. I've put it inside the test string window, and now I'll put in a regular expression. Starting with a straight text match, I've put in super with a capital S. The test string is looked through, and a result is shown. Because all this doesn't fit on the screen at once, I'm going to shrink the test string. As the match result shows the entire message and highlights where the matches are, I don't need both on the screen at the same time, so I'll just be leaving this minimized. When you look at the match results, you'll see the word super is highlighted 3 times. There you go. That's your first regular expression, a plain text match. To see this in action again, I change the word, and sure enough, a similar result. Now the word outfit is matched. Third time's the charm. Now I'm matching fail. Notice that like the regular expression thing that I spoke of earlier, this isn't matching a word, it's matching the text. So the fail in failure and failing gets matched. If you don't include information about the white space inside of the regex, you will get a straight text match, whether it's a word on its own or part of a longer word. How about if there's no match? Let me put in another string, and the tool tells you there are no matches. A plain text match is useful, but not particularly flexible. Let me show you how to match a range of characters. The letter T, that's a plain text match as before. Square brackets indicates that I'm going to be looking at a range of information. And here, I'm matching any vowel. So, you're looking for a pattern that starts with the letter T and then one of the vowels. Let's look at some of the matches. The TU in Saturday, the TI in corporation, the TE in uttered. How about up here? What's going on? Well, it's hard to tell inside of this tool, but this is actually 2 matches. TA being the first one and TE being the second. You need to be careful when you're using a tool like Pythex to know when you're looking at a match and when you're looking at multiple matches. It doesn't make a distinction in the resulting screen. You can also match numbers. The hyphen in this expression says that it is matching a range. So this is looking for a single digit in the range 0 to 9. So if you were looking for 4 digits in a row, you put in 4 sets of square brackets with 0 to 9 inside. The match result shows 1095, 1949, 3990, 9230, and 1949 again. Notice the serial number here. There's 7 digits before the hyphen. Because it's looking for 4 digits, it finds the first 4 and stops. If I change the expression to just match 3, now you'll get 923 as the first match and 041 as the second match. Ranges can also be letters. This is looking for the plain text match of colon preceded by any letter of the alphabet. So in the matches, you get E colon, N colon, E colon, M colon, O colon, T colon, etc. Notice that the matching is actually case sensitive. There isn't an example in this text, but if there were a capital letter followed by a colon, it would not match. You can also do ranges on capital letters. Here's another expression. This matches a single capital letter followed by either a capital letter or a small letter. This finds RP, 2 capital letters, ST with a capital letter and a small letter. MIME is showing 2 matches, MI and ME, similar with ASCII, AS and CI. You can also complement a match by using the caret symbol, Shift 6. This says match any character that is not in the range small a to z, capital A to z, so any number or special character will show up. This expression combines the ideas. This is looking for any digit followed by an even digit, or more specifically, not an odd digit, not the digits 1, 3, 5, 7, 9. Matches include 1, 0, 9, 4, 3, 4, and 1A. Notice that it's just not those digits, so letters are included. This is why tools like Pythex are useful when you're building your regular expressions. You may not actually be building the expression that you think you are, and seeing it in some example text will show you whether or not you've built it properly. What if you actually want to match the hyphen symbol? You can see that here. If the hyphen is the first letter inside of the character set, it'll include this literally. So this is a hyphen, or the small letters A to Z, followed by a capital letter A to Z. This matches -R in the XRP, -S, -V, and -T. At the moment in the text, there isn't a small letter followed by a capital letter. If I change the text to include that, now you'll get the NE matching as well. A similar idea is used if you're trying to match the caret symbol. If the caret isn't the first symbol inside of the class, it's taken literally. So this expression says to match the number sign, the colon, or the caret. Part of Wile E. Coyote's cartoon utterance of a swear word is being matched. Notice this is actually 2 matches, the number sign and the caret separately. Other colons in the text are also being matched. To match square brackets, you include those inside of the square brackets. This regex is 3 pieces. The first part is the character left square bracket. The second part is a capital letter. And the third part is the right square bracket. Combined, these match square bracket x square bracket inside of the model number. Alternatively, you can use the backslash to escape the special character. \left bracket and \right bracket tell the regular expression to actually look for left and right bracket characters, matching the bracket x bracket in the model number below. You have to be very careful with this. Escape sequences are used in Python strings to escape other kinds of letters. So when you have a string containing a regular expression, you can end up with escape sequences of escape sequences. This can be a little messy. I'll show you how to deal with this later. One last example for you inside of character sets. You've seen this before. It's matching the capital letter A or the capital letter C. There's another way of expressing this concept. The pipe operator acts as OR, so this expression is equivalent to the previous one, using either the letter A or the letter C. With a short expression like this one, it doesn't make much difference which mechanism you use. When you start to do more complicated mechanisms and grouping things together, the OR symbol allows you to do things that square bracket character sets does not. So those were your first regular expressions. Hopefully it wasn't too painful. In the next lesson, I'll be talking about metacharacters, how to express things like white space inside of a regular expression. In the previous lesson, I introduced you to this simple, plain matching regular expression, and then added some complexity with ranges of characters and class matching. In this lesson, I'll be talking about metacharacters, special characters that represent things like white space in a regular expression. First off, a little bit of review. A plain string match is the text you're looking for. In the sentence, I put the thing in the place, thing is highlighted because the regex is thing. Do note that it's only those letters, not the surrounding white space. Similarly, for the pattern spam, well, there's spam, eggs, sausage, and spam, that's not got much spam in it, has 3 matches, each of the instances of spam. Character ranges or classes allow you to specify a match over a range of characters. A common use for this is to look for numbers. The square brackets indicate a range, in this case 2 ranges, both 0 to 9. That matches the number 42 in the text on the right-hand side. You can match with letters as well. Inside of the square brackets, I'm looking for small a to z or large a to z, so essentially any letter, followed by the plain text AR. So far, bar, and the par part of subpar matches. Regexes support something called a metacharacter, for example, digits, white space, words, etc. Oftentimes, these are shortcuts which you would otherwise have to specify with a lengthy square bracket class. Here I am back inside of Pythex, using the same text to search through as before, the Wile E. Coyote email message. I'll start with a character class. This is any vowel. And now I'm going to introduce the first metacharacter, period. Period means any character, except for a new line. So now, with the character class vowel, period, character class, you will see matches where it is a vowel, some other character, and then another vowel. If you look at the matches, this includes things like a less than a, exa, ilu, ase, etc. Because period is a special character, if you actually want to match one, you have to escape it. This is similar to the square brackets that I showed you in the last lesson. Here's a letter, followed by a period, followed by another letter. This matches parts of the email addresses in the to and from headers. Here I'm matching quote followed by any character. If you look carefully, one of them's missing. This quote isn't highlighted, and that's because the period does not actually match new line, and as the only character after this quote is a new line, it won't match. A common pattern that you would need to match in programming text is the small letters, capital letters, digits, and an underscore. In most programming languages, these are the valid characters that can be inside of a variable name. Here you can see the plain text match for the capital letter E followed by that range. In the case of this email message, that matches the EN in enclosed. Because this is so common, there's a shortcut for it. \W is a metacharacter, short for word, and in this context, word means a programming variable. This metacharacter does the exact same thing as the previous expression, still matching enclosed, but is far less to type. A common pattern with most of the metacharacters is for the capital version of them to be the inverse. Changing small w to capital W matches everything that isn't a word. In this case, we have capital E followed by white space, greater than, and hyphen, whereas greater than, hyphen, and white space are not alphabetic letters or digits or an underscore. Speaking of digits, you'll remember this pattern from the previous lesson. It's looking for 4 digits in a row. Again, because this range is common, there's a shortcut for it as well, the metacharacter D. 4 \Ds in a row is the same as the previous expression. And like the \W, capital D is the inverse. This pattern is looking for a digit, followed by a non-digit, followed by another digit. This matches the 3A3 and the 1.0. Keep in mind that non-digit means every character except for 0 to 9, so periods and hyphens are included. \s, short for space, matches space characters or white space inside of your text. These are things like space, tab, and newline. This particular tool doesn't actually highlight the newline characters, which makes it a little hard to see, but if I look for colon followed by white space, you'll see what I mean. The email headers all have colons and spaces, so those match just like before, but the product information was as follows, has nothing after this, it's just a newline character, so you can see that this is matching the white space of the new line. Like before, capital is the inverse, everything but a white space. So one way of finding the 4-letter words is white space, followed by 4 instances of non-white space, followed by white space. This of course will match letters from the alphabet, punctuation, and digits. You can use metacharacters inside of a character class. \d matches a digit. The square brackets give the option of matching either a hyphen or a \s. Remember, if the hyphen is first inside of the character class, it's a literal match, not a range. So this is looking for a digit followed by either a hyphen or a white space. This matches things like the 0 and the 9 at the end of this line, because the carriage return is included, as well as the 3 followed by the hyphen, and the 3 followed by the white space, the new line. Because metacharacters begin with a \, to look for a \, you must escape it with another \. This is looking for a literal \, followed by a digit between 0 and 9. It matches the \5 at the end of the model number. This can get rather confusing when you start combining things. This is the same pattern as before, but instead of using the character class, I'm using the metacharacter for digit. So the first 2 backslashes are an escaped \. The third \/ is part of the metacharacter \d. This is looking for a literal \/ followed by a digit. And this once again matches the \5 at the end of the model number in the text. Next up, I'll be talking about anchoring expressions, ways of making sure that the thing you're finding is at the beginning or the end of a string. In the previous lesson, I introduced the concept of a metacharacter, a way of describing groups of characters through shortcuts like white space. In this lesson, I'll be talking about anchors. Anchors allow you to change where in a match happens, the beginning or end of a string. The first metacharacter that I introduced you to was the period. Period means any character that isn't a new line. In this text, the core of it, a cur can't drive a car, C.R matches the COR of core, the CUR of cur, and the CAR of car. \W is the word character, which is all letters, digits, and the underscore. The regex on the left is looking for a B, then some word character, some other word character, and then an R, matching bear and beer in the sentence on the right. All of the \/ metacharacters support capitalization being the inverse. The regex on the left has 3 word letters, followed by a non-word letter, followed by a digit. This matches the model numbers on the right-hand side. A, 3, F all match the \w, colon matches the \W, and then the 3 for the \d. Same goes for JHK \2 and 23M/1. \s is the metacharacter for white space. Literal ARK followed by \s, \w matches ARK space WA and ARK space AN in the arc was large and inside it was dark and scary. To match a backslash character, you need to escape it with another backslash character. This can get a little messy. Looking at this code, you see metacharacter \w, a literal colon. The first two backslashes that follow are an escaped backslash. The third one is for the metacharacter w, followed by another metacharacter w, followed by another, followed by an escaped backslash, and then 3-digit metacharacters. This matches the portion of a Windows path on the right-hand side. Up until now, all the matches have been anywhere in the string. An anchor allows you to choose whether or not it matches the beginning or end of a string. You can also change the behavior of the regex by putting it in multi-line mode. Multi-line mode changes whether or not a new line is considered the beginning of an anchor match. By default, it's only the beginning and end of the string. In multi-line mode, it's the beginning, the end, and any new line, allowing you to treat paragraph breaks as if they are the beginning of new strings. I'm back inside of Pythex using the same Wile E. Coyote email message. The first anchor I'm going to introduce you to is the caret symbol. You may remember that the caret symbol inside of square brackets negates the square brackets. Unfortunately, although it's a little confusing, caret also means something completely different outside of the square brackets. It means anchoring to the beginning of the string. Caret capital X says look for a capital X at the beginning of the string. The caret meaning the beginning. If I change this to caret capital P, no match is found. This is expected. The string begins with capital X. If I turn on multi-line mode, the behavior changes. Now, the P in product is matched. This is because in multi-line mode, anchors match to the beginning of paragraphs. So if the line before ends in a carriage return, it's considered like the beginning of the string. This is pretty useful if you're doing multi-line text like this. Essentially, it becomes a line that begins with rather than the entire string begins with. There are two metacharacters for doing this kind of match. Caret is one of them. The other is \A. \AX matches the X at the beginning of the string, but \AP does not match even though you're in multi-line mode. That's because multi-line mode only affects the caret. Caret and \A work the same way if multi-line mode is off. When multi-line mode is on, \A still only matches the beginning of the string. The next anchor that I want to show you is $. $sign means the end of the string, or if multi-line is on, the end of the line as well. Remember that period itself is a metacharacter, so to match a period I have to escape it, and the $sign says at the end of a line. Because I'm in multi-line mode, this is matching the end of the sentences. Turning multi-line mode off, the match is only the one at the end of the string. Similar to \A is \Z. It anchors to the end of the string whether or not you're in multi-line mode. The last anchor I'm going to introduce you to is \B. This is the word boundary. \B, literal F, looks for words that begin with the letter F. You can also match things at the end of a word by having the literal ER followed by the word boundary. Finally, you can invert it by capitalizing the B, looking for non-word boundaries. So non-word boundary, ER, non-word boundary, matches ER inside of a word. That's regex anchors. Next up, I'll be talking about how you can repeat expressions with quantifiers. In the previous lesson, I showed you how to use anchors to change where the matches happen inside of a string. In this lesson, I'm going to be talking about quantifiers, how to do repetition inside of your pattern matches. First, a little review. The first anchor I showed you was the caret symbol. caret THE matches the at the beginning of this string. Turning on multiline mode, and the gets matched at the beginning of each of the sentences in this string. Replacing caret with \A, even in multiline mode, only matches the beginning of the string. Now to the other end, $ matches the end. Like the caret, in multiline mode, $ matches the end of a line. \Z is the equivalent of \A, matching the end of the string even in multiline mode. In addition to the beginning of end of strings, you can match word boundaries. \B is the word boundary anchor. Literal CAR \B matches car but not carpet, because car ends on a word boundary. You can invert that behavior with \B. Now CAR \B matches carpet because it doesn't end on a word boundary, and it no longer matches car, which does. You can look for repetitions of patterns inside of your matches using a quantifier. There are 4 kinds of quantifiers. Star means 0 or more matches. Plus means 1 or more matches. Question mark means 0 or 1 matches. And curly braces indicate some number of matches between M and N, including M and N. To start out, let's look at the plus symbol. 3, 9 plus 0 looks for repetitions of the number 9, so literal 3, 9, 1 or more times, and then 0. This matches 3990. Changing the plus to a star, and the number of matches changes. This says 3, then 9, 0 or more times, and then the number 0. Changing the star to a question mark, and now you're looking for 0 or 1 matches, so only the serial number matches. The model number has 2 9s in it, so it no longer qualifies. This quantifier doesn't include 2 9s in a row. Quantifiers can also apply to metacharacters. This regular expression is the literal s/n: space, followed by the digit metacharacter 1 or more times, then a hyphen, and then a word character. This can be used to match the serial number inside of the text. You can also apply quantifiers to character classes. \B is the word boundary anchor, so this regex is looking for something separated by word boundaries, what we would consider a word. The first character class is just the vowels, indicating that this word begins with a vowel, and then 0 or more small alphabetic characters. This matches all of the words in the text that begin with a vowel. When dealing with quantifiers, you need to understand the concept of greediness. This is less than some character 0 or more times, and then greater than. This is creating one match, starting with less than, some number of characters, and then greater than. The 2 greater than characters buried inside of it are eaten by the quantifier because it's in greedy mode. It will consume as many characters as it can inside of the regular expression. You can modify the quantifier by changing it to non-greedy mode. Adding a question mark after the quantifier changes it to be non-greedy. Now you're seeing 3 different matches, each starting and ending with angle brackets. It's unfortunate that they chose question mark as the way of turning something from greedy to non-greedy. Question mark on its own is also a quantifier. This makes regular expressions a little difficult to read because the context of the character changes what it means. Here's another example, this time using the plus quantifier. Remember, that means 1 or more. This is looking for a capital A and a small a repeated 1 or more times. This matches the ah in ah huh. Because it's in greedy mode, it absorbs all of the letters. Adding the question mark, and it takes the minimum number to make this expression valid. Because the plus means one or more, the minimum is 1. So now just capital A and small a matches. This concept can be a little confusing when dealing with the question mark quantifier. This is the capital A followed by the small a 0 more times. This is matching the A's in ASCII and ACME and after, but it's still capturing the first two letters of ah. Changing this question mark to non-greedy mode. And notice the difference in ah. Now only the capital A is matching. The least greedy version of 0 or 1 characters is 0 characters, so only the capital A is highlighted. This is referred to as a zero-length match. The other kind of quantifier indicates the number of repetitions. This is done with curly brackets. This is looking for whitespace metacharacter, a digit, and the digit being repeated 7 times. This matches the beginning of the serial number. You can also specify a range of matches. This regular expression now looks for a space followed by anywhere from 2 to 7 digits. This matches space 1095, space 18, space 1949, as well as the serial number before. A range like this is inclusive. The 7 isn't the upper limit, but the largest number of values. This is a little counterintuitive for people who spend a lot of time programming, where normally these kinds of comparisons are less than rather than less than or equal to. It takes a little getting used to. The second value doesn't have to be specified. This version says look for 4 or more digits. The first value also doesn't have to be specified. This says from 0 up to and including 5 matches. The white space all the way through the text is being highlighted because white space followed by 0 digits is matching this expression. Not only can you remove the bottom end of the range and the top end of the range, you can remove the entire range. This is equivalent to the asterisk quantifier. If you're looking to match actual curly brackets, don't put in a number. This will match literal curly brackets. Because there's no number and no comma inside of it, it treats them as if they are normal characters. Like other quantifiers, the ranged match is also a greedy match. The ah in ah is matching all 9 of the A's. You can modify the match by applying the question mark. Now it's only matching the first 6 A's. The least greedy version of this expression is matching 6 characters. Next up, I'll show you how to group parts of expressions and examine matches on subsections of a string. In the previous lesson, I showed you how to multiply your regular expression using quantifiers. In this lesson, I'll show you how to group parts of your regular expression together in subsets. First, a little review of quantifiers. The asterisk quantifier means 0 or more. So 67 star 3 matches any number of 7s. 3 7s, 2 7s, 1 7, and 0 7s on the right-hand side. The plus quantifier means 1 or more. So the match on the right changes. The first 3 are the same because they have 1 or more 7s, but the last one no longer matches. 0 7s is not 1 or more. Question mark means 0 or 1 matches. This affects the right-hand side, with the third grouping of numbers having a match and the fourth grouping having a match, with 1 7 and 0 7s respectively. By default, quantifiers are greedy. The angle brackets, similar to what you would find in XML here, with a dot star inside of it, consumes the entire angle 2, 3, and angle 4 on the right-hand side. The right angle bracket after the 2 gets consumed because this is a greedy match. You can change the match to be not greedy by adding a question mark. This splits it up into matching the two pieces of XML, probably closer to what you were intending in the first place. Greediness also applies to the plus quantifier. Changing it to not greedy consumes fewer digits. The 77 turns into a single 7, and the 48348 turns into a single 4. The not greedy version of 1 or more is 1. Question mark means 0 or 1 matches. The not greedy version of this means 0 matches. Not greedy of 0 and 1 is 0. Curly braces indicates a number of matches. Brace 3 here says look for 3 matching literal Bs. You can put a range inside of the braces. This is 2, 3, or 4 matches. It is inclusive. If there are no numbers, the braces are taken literally, matching C curly brace A on the right-hand side. The not greedy version of this consumes the least number in the match, in this case 3. Regular expressions allow you to group parts of a pattern together. This grouping gives you access to portions of a match. By grouping things together and combining them with a quantifier, you can create strings of repeated sequences. You can also use a mechanism called back references. A back reference is a reference to a previous grouped match inside of the expression. I'm back inside of Pythex, once again using the Wile E. Coyote email message for testing. Here's a regular expression of the literal 1 and any digit. As expected, this matches a whole bunch of parts of the text. You can create groups of expressions by using parentheses. Here's the same expression inside of a group. The matches in the text are the same, nothing's changed, but now, on the right-hand side, you have access to the groupings of matches. Pythex shows these and allows you to get at each one of them. When doing this in Python, you can pull out these multiple parts from a single match result. Here I've combined a group and a class. This is the literal letter B, and then a grouping of any of the vowels repeated 1 or more times. This matches the BE in September and beyond, and the BOO in boomerang. Notice that the plus is inside of the group. This means the repetition is on the vowels. On the right-hand side in the match captures area, you can see the vowel portions of the match. Though the B is highlighted in the text, only the group portion is shown in the match on the right-hand side. Changing the position of the plus changes how this expression works. Now you have the B as before, the class with a vowel in it, and it's the group that repeats. The matches in the text on the left look the same, but the groups on the right-hand side are different. Particularly, match 3 used to be OO because the plus was on the inside. Now with the plus on the outside, the group is being repeated, and the group is only matched once. Backslash with a number is a back reference. This is looking for a match the same as a preceding group. Backslash W inside of parentheses matches a word character. Backslash 1 looks for whatever was matched in that group. So this regular expression is looking for the same 2 letters in a row. You can see this in the text in the AA and the BB, as well as the 99 in the model number. Remember that /W does both alphabetic characters and digits and the underscore. The grouping is around only the single letter, so the match captures section on the right-hand side only has the initial match. The back reference provides the other portion of the regular expression. Well, that was fun. Here's a little more of a challenge. Break the regular expression down to parts. Look at the first \b and then another \b. Those are anchors looking for word breaks. So the group inside is something that is a word separated by spaces. \w metacharacter means a letter, a number, or an underscore. The curly braces indicate that this will be repeated 3 times. So the first part of this regular expression says a three-letter word separated by word boundaries. Dot star consumes 0 or more characters, and then \1 is a back reference to whatever was in the group. So whatever's matched as this three-letter word, some amount of text, and then that text appearing again. This happens 3 times. The first match is with the you and ending in the you portion of your in the first sentence. The second match is the, ending with the a little later, and the third match again is a pair of thus. Inside of the match captures, you can see the portions of the group being pulled out, so you can see exactly what word was repeated. Pay particular attention to the first sentence. There's something a little subtle going on here. Although the first part of the match is looking for a word surrounded by a boundary, what is inside of the group is just the letters, so the group contains YOU. The bigger part of the expression outside of the group includes the word boundaries, but the back reference of match 1 is only on the YOU. It will match YOU at the beginning of the word your. You've seen enough of regular expressions, the language inside the language. Now it's time to actually see how to use them in Python. In the previous lesson, I finished up the language of regular expressions and introduced the concept of grouping. In this lesson, I'll be showing you how to use regular expressions inside of Python. First, a little review. The regex on the left has some grouping in it. The square brackets indicate a character class of the vowels. The parentheses around it are a group of that choice of vowel. And the R is literal. This highlights the AR, OR, and ER in the string, creating 3 groups matching an A, an O, and an E. Later, when I show you how to do this in Python, you'll actually be able to access this content. Here's another one. This time a character class of the digits 4 to 9, and that is grouped, and then 1 or more of those can happen using the plus quantifier. Notice that this matches the 4, 5, the 9, and the 8, 8, 8, but the grouping is the 5, the 9, and the 8. When you apply a quantifier to a group, only the last group gets counted. So the 4 and the 5 matches the regex, but the 5 ends up in the group. The 9 matches the regex and ends up in the group, and the 3/8 matches the regex, and the last 8 ends up in the group. This regex looks for the literal letters THE grouped together, can have 0 or more repetitions of any character, then uses a back reference. So you're looking for whatever matched the first group happening again inside of the string. So what you're getting is a match between the words the. All of the red text matches, but only the ends up in the group. You've been pretty patient with me up until now. Everything's been about regexes without really talking about Python. So now I'm going to show you how to use this inside of Python. The RE, short for regular expression library, is a standard part of Python. Most of the methods inside of the RE module take a string pattern, which is the regex, and a string to search against, and return a result. The result is usually a match object. This match object gives information about the match, whether or not a match happened, and what portions of the string matched the result. Match objects are truthy. That means they can be compared as booleans, so you can use a regular expression method that returns one of these objects and then compare the object in an if statement to see whether or not a match happened. I'll start out by importing the module. This question will be my test string. Using the search method inside of the RE module returns a match object. In this line, I've searched for the literal expression SPAM inside of the question. As a match object was returned, that tells you that spam was successfully found within the question. The span parameter inside of the match object tells you where the match happened. This is between letters 7 and 11. The numbers in the span are equivalent to a slice in a list or a slice of a string, so this indicates that it starts at 7 and finishes at the 10th. 11 is the upper limit, not included. This is the opposite of the curly brackets inside of the regular expressions themselves. It can be a little confusing as you switch back and forth between the two mechanisms, but the span parameter of the match is closer to the Pythonic mechanism. Here you can see I've sliced question using the 7 and 11 from the span, and I get back SPAM, the match from the string. I'll do that again, this time storing it in a variable. Evaluating this variable as a Boolean returns true, indicating that a match was found. I can run a function called span on the match object that returns the lower and upper boundaries. Another function called start, showing the lower boundary. And finally end to give you the upper boundary. The string attribute shows you what was being matched against. Somewhat confusingly, the RE module also has a function called match. To be clear as I'm moving forward, if I'm talking about the function, I will be explicit and say the match function. Otherwise, I'm talking about a resulting match object. The match function matches the beginning of the string. This is the equivalent of using a caret anchor inside of your regex. This did not return anything, and that's because no match was found. Let me do that again, this time storing it in a variable. The variable doesn't contain anything. Comparing it to none shows that it's true. Or, converting it to a Boolean means it's false. This shows you how you could test the results of your regular expression functions inside of an if statement. This regex was successful. It's looking for the repetition of 5 word-like metacharacters. As the string starts with LOVEL, which are all word characters, the match results, showing the span of 0 to 5. Python 3.4 added a function called fullMatch. As you might guess from its name, it's looking for a regular expression that matches the entire string. Of course, looking for spam, that's not going to match the whole string. So once again, you're getting back a none object. Let's break this regular expression down. Looking at the inner group first, there's the word metacharacter with 0 or more instances. There's the whitespace character with 0 or more instances. So I'm looking for something that looks like an actual word. That is inside of a group. That group repeats itself 0 or more times, and then is followed by an exclamation mark. All of that is grouped. The outside group can be repeated 0 or more times. This is successful because it matches the 2 subparts of this string, lovely spam exclamation mark and wonderful spam exclamation mark, each match the outer group, and because the outer group is repeated, this regular expression matches the entire string, giving a truth value for full match. Another function the library has is findAll. Unlike the other functions I've shown you so far, findAll doesn't return a match object, it returns a list. It applies the regular expression and finds each match inside of the string, returning the matching characters in a list. This regular expression is looking for a vowel followed by not a vowel. Inside of lovely spam, wonderful span, you have OV from lovely, EL from lovely, AM from spam, etc. FindAll returns a list. Sometimes, instead of wanting a list, you want an iterator. Enter findIter. It essentially does the same thing as findAll, but returns an iterator instead of a list. This is more efficient in memory if you're doing a large number of matches. Well, that was your first exposure to using regular expressions inside of Python. Next up, I'll show you how to take advantage of grouped results. In the previous lesson, I showed you the RE module of Python, the module that exposes the power of regular expressions inside of Python code. In this lesson, I'll show you how to get at those groups defined in your regex. You've already seen some of the attributes and methods on the RE match object. There are other ones, though, around grouping. The group function takes a list of arguments. It returns a tuple of matched groups for each of the numbers you give it. So if you call .group1, 3, it'll return the first and third match in a tuple. Groups plural returns all of the matched groups. You've seen the start and end methods showing the beginning and end of matches in the string. The expand method takes a string template and substitutes any back references inside of the template with their actual results. This is kind of like the idea of an F string, but with the back references from your regex. Finally, there's also the span method, which you've seen before as well, which contains the start and end values in a tuple. Starting out by importing the library, let's do a search with a group match. This regex is looking for a group consisting of one or more word metacharacters, followed by a comma, followed by another group with one or more word characters. The groups function shows the matching groups. The first group is the word 1, O-N-E, and the second group is the word 2, T-W-O. You can see an individual group by passing a number to the group function. You can also pass in multiple. If you pass in more than one, you get back a tuple in the order that you put it in. You may notice that these are all one referenced. This is to be consistent with the concept of a back reference. Group 0 is the entire match. Because this regular expression is looking for some number of metacharacters, a comma, and then some number of metacharacters, the 1 and the 2 match, but the 3 does not because there's only one instance. You can also use indexes on the match object to get the same content. Once again, this is the back reference 1. 0 is the entire match, just like match.group. Expand gives you a template to be able to expand back references. This takes the results of the match and then inserts the back references that you reference inside of the template into the string. This is kind of like an F string for your regular expression matches. You've seen the start, end, and span functions before, but for completeness' sake, here they are again. There's a plain text search. There's the match. Starting value of 4. Ending value of 7. And the span of 4 to 7. Just as a reminder, these are 0 indexed, the same as a slice in a list or a string. Next up, I'll show you how to name groups so that you don't have to just use numbers. In the previous lesson, I showed you how to use our regular expression in Python with groups and getting at the group data. In this lesson, I'm going to show you an advanced version of grouping where you can name the groups. First, a little tangent. You may recall that Python uses backslashes to escape special characters inside of strings. For example, \t and \n are the tab and newline characters. If you want a backslash inside of a string, you have to escape it with another backslash. This string would only show a single backslash if it were printed out. This escape mechanism is the same escape mechanism that regular expressions use. This can be messy. You end up having to escape your escape sequences in order for them to work properly inside of the regex. Let's go into the REPL and I'll show you what this means. So here's the first regular expression, looking for metacharacter W one or more times and a comma. This matches 1 and comma. So why haven't I brought up this backslash problem before? Well, Python tries to be smart about this. If you put a backslash into a Python string and have it escape a character that is not a valid escape character, Python automatically turns that into a literal backslash. This only gets complicated when you overlap between the escape sequences in a string and the escape sequences in a regex. To be proper, I should have been using 2 backslashes. Both of the matches are the same in this case. This gets complicated when you're looking for backslashes. The string being searched, the second parameter, is the word 1, followed by a literal slash, denoted by 2 backslashes to escape it in the Python string, followed by the word 2. The regular expression, metacharacter w plus backslash and the word 2 fails to find anything. This is because the 2 backslashes in the regular expression get turned into a single backslash to the regex module. It sees \t and interprets that as a tab, not matching the string on the right-hand side with the literal backslash. In order to find the actual backslash, you have to escape the backslash in the Python string and escape the backslash in the regex. This results in 4 backslashes. The first 2 backslashes escape a single backslash in the Python string and pass a backslash to the regex module. The second 2 backslashes do the same, resulting in the regex module receiving \\, which is the regex escape for a backslash. This is an escape of an escape. This will actually find the match in the string on the right-hand side. Python automatically converting a non-escape sequence backslash into a real backslash is neat to have, but can cause all sorts of problems and ambiguity, so you have to be careful with it. If I hadn't been looking for the word 2, but I'd been looking for the word 8, I would have had a much bigger problem. Ooh, and there it is. Let me scroll up so you can see that again. Take a look at this regular expression. The first backslash gets automatically converted by Python into a backslash character, and that gets passed into the regex as the meta w. The second 2 backslashes get escaped, turning into a single backslash character, and there is no \e. There's no meta character that uses the e. So the regex module throws an exception. In order to match the \e in 8 on the right-hand side, you will need 4 slashes. Here's how to do it right. And that's the match you're looking for. I generally don't recommend taking advantage of Python's automatic conversion of those backslashes. You should match for what is there. A better choice is to use a raw string. This is a feature built into Python that says this string doesn't have any escape sequences in it. Here's an example. When you look at the value of the content variable, you'll see that Python has turned this into the escaped backslash. Your best practice is to use raw strings everywhere with your regexes. This makes it far easier to understand as you're coding along. To summarize, both regexes and Python strings use backslashes for special characters. That becomes complicated when you're using a string to describe a regex. Inside of a regex, you should always specify the double backslash for the meta character to be safe. If you're searching for an actual backslash, it needs to be escaped twice, once for Python and once for the regex. Or alternatively, just use a raw string. It's far easier to read and understand. It's time to go back into regex groups. So far, you've seen groups with numbers. You can also use named groups and non-capturing groups. I'm back inside Pythex. Time to look at named groups. I hope you're comfortably seated. The regexes are only going to get longer and longer and more complicated. Here's your first named group. Let's break it down together. On the outside of the regex is metacharacter S. So you're looking for something that is separated by whitespace. Between the whitespace characters is a grouping. The part you haven't seen before is $P angle brackets. This is the named group. $P indicates that it's a named group. What's in between the angle brackets is what the name is. So in this case, the name is C1. The remainder of the group is the regular expression, as before. This particular expression has a character class of non-vowels, a character class of small alphabetic letters, and that second class is repeated one or more times. On the right-hand side, just like before, you can see the match groups, but now, instead of them being numbered, they're named. There's only one group here named C1, so every match has C1 in front of it instead of 1 like before. Here's another one. This is actually the same regular expression twice in two different named groups. The first group, $P, says it's a named group, named C1. The second group, $P, named C2. This regex is looking for the same pattern twice in a row, separated by a whitespace character. Both these groups are looking for texts that don't start with the small vowels. Match captures shows the two named groups showing up in the result. The first result is in the subject line, suit failure, with C1 being suit and C2 being failure. Here that is inside of Python. Content is the text to be searched. Here's the regular expression. I'm going to pause for a moment here, see if you can figure out what will be in the groups. The match object shows you the portion of the string that matches, which is the 1, 2, 3. And calling groups returns the values of 1, 2, and 3. I'm going to rewrite the exact same regular expression, this time using named groups. So you see the capital P inside of the group to indicate the name, and I'm naming each of these groups first, second, and third respectively. Match.groups has the same content. There's another method that I haven't shown you before, which is groups Dict. It returns a dictionary with the named contents. So now I've got a mapping between first, second, and third in the regular expression named groups with the values of 1, 2, and 3, which is the content of the matched groups. This is a bit of a trade-off. It makes your code easier to read because you're actually naming what you're looking for rather than 1, 2, and 3, but it tends to make the regular expression harder to read because your group has the extra content in it to specify the group name. Back inside of Pythex, here's a quick review of how back references work. The group here contains a metacharacter W, and the \1 is a back reference which refers to the first group. Same thing goes with a named group. This group is named twice, and \1 is a back reference that works the same as before. You can also name a back reference. $P with an equals says to use the named back reference. Everything between the parentheses here is the equivalent of \1, the back reference from before, but this time it uses the named reference twice. Here's another set of groups. There are 3 groups here. The first is a non-vowel. The second is a character class with 1 or more vowels, and the third group is a non-vowel. If you look at the matches on the right-hand side, this matches things like SEP for September, to : SUINT for suit. So far, so good. What if you're not interested in the piece in the middle, but still need the grouping to be able to match the expression? $: says this is a non-capturing group. The matches for the regex are the same as before, but the groups in the match captures on the right-hand side are different. So notice before there were 3 groups for each match, now there are only 2. This middle group is not capturing. This can be useful for a couple reasons. One, if you're doing a lot of regex work, each group takes up some memory, so a non-capturing group tends to be less expensive. It's also useful to use groups for repetitions or keeping a chunk of characters together. Essentially, it might be easier to write the regular expression using a group. If you're not actually going to use the subcomponent group from the expression, then making it non-capturing will be more efficient. In the next lesson, I'll introduce you to even more of the methods inside of the RE module. In the previous lesson, I showed you how to name your groups. In this lesson, I'll show you even more methods of the RE module, including substitution, splitting, and escaping. First, a quick review of named groups and non-capturing groups. The regular expression on the left is a named group. $P indicates a naming, with the angle brackets surrounding what you're going to name it. So the expression on the left is called digits and is looking for \d plus as its matching criteria. In the sentence, that matches the digits 1, 2, and 3. Those digits are inside of the named group, and so the match results with a named digits containing 1, 2, and 3. Inside of the regular expression, instead of using a numeric back reference, you can use a named back reference. $P equals is the named back reference. The first part of the regex is the same as before. The second part is a back reference using the named grouped digits. From the number 13 through to the number 13 in the string is the entire match, but the group named digits only contains 13. $: is a non-capturing group. The regular expression on the left-hand side has 3 groups in it: literal A, non-capturing R, and literal E. This matches the ARE in care of the string. But only 2 groups are found, the A and the E. The R in between doesn't capture. Here are the matching functions you've seen so far. re.search looks for a regular expression inside of a string. re.match looks for a regular expression matching at the beginning of a string. Full match evaluates whether or not the string fully matches the regex. Find all looks for all of the matches for a regular expression inside of the string and returns a list of those matches. And find iter does the same thing, except instead of returning a list, it returns an iterator. The module has some other functions that may be of use to you. You can do substitution using sub and sub-n. And there are utility functions like split, which is similar to the string split function, but operates using regular expressions. And the escape function, which is useful when you're trying to escape strings with regular expressions in them. Content is a string to search within. And I'll start with the sub command. Sub takes a regular expression, something to replace it with, and the thing being searched. In this case, the regular expression is 1 or more digits. The replacement is the literal number sign, and content is the string to be substituted. It returns a new string with, in this case, the numbers replaced with number signs. You can limit how many times the match happens. In this case, only the first substitution was performed, and then it stopped. Instead of providing a literal string for substitution, you can also provide a function. Function always takes a match object, and then you return whatever you want to have substituted. You'll recall that group 0 returns the entire string match, and then I'm slicing it :-1, which is a Python trick for reversing the string. Using this function inside of sub, and the 2 numbers that are found are replaced with their values of the digits reversed. Back references are also valid inside of substitution. The string is replaced with the first group second and the second group first, resulting in the string 2, 1. There's a little bit of ambiguity in this definition. Let's say I wanted to replace the string with the back reference and then the number 0. There's the back ref, the 0, and the string, and a problem. If you read the error, it says invalid group reference 10 at position 1. The regex library has no way of knowing that you intended this as \1 and then a 0. It sees \10. There is no group 10, there's only one group. You can get around this by using the group metacharacter, \G. The angle brackets say what group to be named. In this case, it's saying replace with group 1 and then put a 0. Another nifty trick with re.sub is what happens when a 0-length match is used. Looking for 0 or more x's in the word spam and replacing it with a hyphen results in hyphens inserted after every single letter. What's happening here is every single spot in the string is a 0-length match, so a hyphen is being inserted inside of each 0-length match. The sub_n function is the same as sub, except it returns a tuple. The first member of the tuple is the result string from sub, and the second member of the tuple is the number of substitutions that happened. In this case, there were 5 dashes inserted. This is the split function from the string library. Passing split a comma splits the string up based on those commas. It returns a list of the components of the string. The regex library also has a split method, allowing you to split on things far more complicated than the string library supports. Here I'm splitting on one or more digits. Like the string library, the re.split method returns a list. Because the 13 and the 42 are the split points, the only contents of the list are the parts outside of the matching patterns. The split method also supports a max split parameter. With max split set to 1, the first regex match is used as a splitting point, and then it returns the rest of the string. If you want to include the split points in the result, use groups. Now the returned list is split on things before the match groups themselves, between the matches, the match group itself, and after the match. This is a neat way of demonstrating non-capturing groups. By changing the expression to a non-capturing group, the end result is the same as without the groups themselves. Next up, I'll demonstrate the re.escape method. Here's an example of searching for 2 to the power 4 in the string. Find all is returning no matches. That's because caret is an anchor. Having something before the anchor that means the beginning of the string doesn't make a lot of sense, so 2 caret 4 isn't being found. Knowing this might be a problem, you can use the escape method. The regex variable now contains an appropriately escaped string. re.escape knows that caret is a special character and creates the correct escape values. Just to show that it works, passing it into findAll, and there it is, it found it. One last thing that I want to show you is the compile method. Under the hood in Python, when you call a regular expression, it compiles that into a binary representation of what you're searching for. You can ask the Python library to do that ahead of time with the compile function. Digits RE now contains a compiled version of the regular expression inside of the quotes. Inspecting the variable just tells you that it's a compiled version of that regex. You can now run all of the functions that you normally run directly in the RE module on this compiled regular expression. This is the search from before, but instead of passing in the regex, you're using the compiled regex and the search method on it. The result is the same as before. Compile is often used if you're going to reuse your regular expression. If that digits regex needs to be used over and over again, you can compile it into a variable in one place and then keep using that variable. Technically, you could do the same thing by storing the regex itself in a variable. This works equally well. You might think that compiling it makes it more efficient, but it turns out that when you run the RE methods, Python is compiling it underneath anyways and caching the result. So if you reuse it, it will still use the compiled expression. The efficiencies are about the same. In the next lesson, I'm going to show you how to use flags to modify the behavior of your regular expressions. Insert your own Sheldon Cooper joke here. In the previous lesson, I introduced you to some other methods inside of the RE module. In this lesson, I'll show you how to use flags to modify your regular expression behavior. Most of Python's regex methods support additional flags to control how they work. An example of this would be changing a regular expression from being case-sensitive to case-insensitive. You do that by setting a flag. All these methods that you've seen before also support the addition of modifying flags. Most of the flags have both a short form and a long form, so you can pass it in as either re.I or re.ignoreCase. As you can tell from the naming of this one, when present, it changes the regular expression to ignore case. You've seen me use the multiline button inside of Pythex. What that's actually doing is setting the multiline flag inside of Python. As you may recall, this changes the behaviors of the caret and $sign anchors, allowing them to match on embedded new lines as well as the beginning and ending of the string. In normal practice, the period does not match the new line character. Adding the .all flag allows it to match the new line character. This is one of my favorite features of Python regular expressions. It changes how white space works inside of the regex, allowing you to use multiple lines. I'll show you an example of it later, but it makes it far easier to comment and display what the regex is doing inside of your code. This flag is barely documented. It's documented as being there, but there aren't a lot of details unless you go into the compiler about how it works. It shows debug information about how the regular expression is working. The default character encoding in Python 2 was ASCII. That changed to Unicode in Python 3. The regular expression module changed with it. If you don't specify a flag, Unicode is the default encoding for regexes and the strings being searched. You can control that by setting the ASCII flag or setting the locale flag. The locale flag sets it to whatever the default encoding is for the user's current locale. Start with a simple search, looking for the small letter A with one or more instances. Nothing is found. Adding the flag at the end, and the behavior changes. The match is now case insensitive. If you don't feel like typing ignore case, .I is the short form. You've seen the multiline behavior inside of Pythex. Here it is in Python. And of course, the \A variant doesn't match in multiline or non-multiline mode. This is the same as what I showed you in Pythex. Without modification, the period metacharacter doesn't match new lines. Adding the .all flag changes the behavior of that. I was really happy when they added the verbose feature to regular expressions in Python. It makes the code far more readable. Here's an example. I'm going to start by writing a regex on multiple lines that shows comments about the phone number it's searching for. Pardon my North American bias with the North American style phone number, but this regex matches a phone number with a 1, an area code, and then 3 digits, hyphens, and 4 digits separated by a white space. Without the verbose flag, this wouldn't work. The additional white space would be considered literal characters and would be searched for. Likewise, this isn't the format for a comment inside of a regular expression. I do find this easier to read, though. And to use it, all you have to do is pass in the verbose flag. Here I'm going to compile the expression. And now I can apply that regular expression to a phone number. My friends in Canada will understand why I'm suddenly hungry for pizza. If pizza's not good enough, you could go with breakfast food. Nothing unusual about this, but watch how it breaks if I apply the verbose flag. It no longer matches. The effect of the verbose flag is to make white space non-meaningful. That means the regex on the left-hand side, bacon, comma, space, eggs, is now equivalent to bacon, comma, eggs without the space. When that's applied to the string on the right-hand side where there is a space, a match is no longer found. This means if you are looking for white space when using the verbose flag, make sure to use \s and be specific about it. Now for some fun with the debug information. I'll start with something that works. Here's the string I'll be searching. Here's a valid regular expression. I'm looking for the literal word spam with any character after it and repeating 3 times. It finds it, spam, 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 period. So far, so good. Now let's assume for a moment that you've forgotten that you're supposed to use the number 3, but instead you just typed the word. Of course, that doesn't work, but if you're trying to figure out what went wrong, you can add the debug flag. Wasn't that helpful? As I mentioned before, Python doesn't document this flag very well. It says that the flag is there, but it doesn't describe what the actual output is. I looked for a while and I've yet to find a good article on how all these pieces fit together. But if you read it, you can get a sense of what's going on. The subpattern match there tells you that it's looking for 4 literals, 115, 112, 97, and 109. Those are the ASCII codes for SPAM. The fact that it then looks for the next set of literals tells you it isn't actually looking for curly brackets 3, which is the mistake that I made. It's actually looking for those literal characters. So this gives you a little bit of a hint of what's going on. As I scroll down, you can see this information again. What's marked as line 17 is the hex version of 115, which is hex 73, and it actually shows you that it's ASCII S. You can also see from lines 28 through 40 that it's looking for the literals curly bracket THREE. To see the difference, let's debug the correct statement. You'll notice here that the curly brackets 3 now becomes the phrase max repeat, and it's max repeat with a range of 3 to 3. It's only looking for 3 times. You remember inside of curly brackets, you typically have 2 numbers, m, n. This is essentially the equivalent of m, n, with m and n equal to 3. Once you become familiar with this kind of debug output, and you're expecting to see the repeat sequence show up, when it doesn't, it helps you debug your statement. I don't pretend to fully understand exactly how all of this debug works, but there's enough little hints in it that it can give you an idea of what's going on. In the further reading section, I'll show you a website that actually uses some of this information to help you understand how a regex is working. That's enough esoteric debugging for now. What if you want to combine flags? Here I've used multiline, but I'm looking for !i. I want multiline and ignore case. Each of the flags is a bit in an integer. This means you can combine them using a bitwise OR. If you haven't seen this before, essentially it's the pipe symbol. Multiline, pipe, ignore case, and you get both multiline and ignore case. The match of ignore case $I and multiline finds the I in I didn't after the new line. There's also a mechanism for triggering flags inside of the regular expression itself. The parentheses question mark means to turn the flags on. The I and M here are the single letter representation of the ignore case and multiline flags. You can also turn these flags on later on in the regular expression, but notice it applies to the entire regular expression. Even though the flags are on after the I, it is still doing a case-insensitive multi-line version of I. Later versions of Python deprecate this and warn you that you should only put them at the beginning. I would go one step further than that, and except for a couple very specific use cases, from a readability standpoint, using the flags as a parameter is much better. You can also set a flag just for the duration of a group. You do that with the colon. This says that the group is case insensitive. The first 3 spams match, but the fourth one doesn't, because it can be capital or small s, case insensitive, inside the group, but then literal small PAM. You can also inverse this. Here, the flag on the right-hand side, re.ignoreCase, sets the entire regex to be ignore case. The -I inside of the group turns the ignore case flag off for the duration of that group. This means it will only match small s PAM, overriding the ignore case flag. Hence, the first and last spams don't match. Put your thinking caps on. Next lesson is about some even trickier matching tools. In the previous lesson, I showed you how to use flags to modify your regular expression behavior. In this lesson, I'm going to show you some even more advanced regular expression patterns. I'm going to cover 4 concepts using Pythex: conditional matches, look-ahead matches, look-behind matches, and comments. Conditional matches change the matching behavior based on whether or not something is present or not. Look-ahead and look-behind matches change the behavior of the regex based on content ahead or behind what you're looking for, but don't include that part in the match. And then comments are, well, comments. I'll start with a familiar plain text match inside of a group, looking for the word acme. I can add a quantifier to say that this can occur once or not at all. For the purposes of this expression, nothing's changed. I've added a little more to it. This time it is looking for acme once or not at all. A white space, the word super, and then the period metacharacter 0 or more times. This essentially captures everything in a paragraph after the word acme. Now I'm going to introduce the concept of a conditional. The part that's been added is inside of this group. The question mark with brackets says that this is a conditional group. The 1 is a back reference, so this conditional is conditional on the presence of back reference 1. So if acme, the first group, is present, then this evaluates to true. If acme is not present, then this evaluates to false. The regular expression that gets run in the case of true is everything to the right of the back reference group and to the left of the OR symbol, the pipe. This is the word out in a group. In the case where acme isn't found, the other pattern is run, and in this case it's /w star and fit in a group. You can see the 2 different places where this is happening. The first match has acme, then super, and because Acme is present, it's including the out part of outfit, but only the out part of outfit. In the second case, where Acme isn't present, it's including /w star, which in this case is also out, and the fit part. You can also see how this works out inside of the groups. For the first match, Acme is found and is set for the first group. The conditional is run, so the first part of the conditional is operated, which is the second group, which in this case is out. And the third group, which is the fit, does not get evaluated because the conditional passed. Match 2 has the opposite. The first group is empty. The second group is empty because it's part of the true portion of the conditional. And the third group is run because it's part of the false portion of the conditional. Because group 1, Acme, wasn't found, the second part of the conditional is run, and fit is matched. Now I'm going to show you a look ahead. I'm going to start out with a regular expression without a look ahead in it. I'm looking for the word writing, some white space, and then the literal letter T inside of group. I change the group to be look ahead behavior using the question mark equals operator. What happens here is the regular expression is still looking for writing white space T, but the question mark equals T portion is not consumed. No group is created, and more importantly, the T isn't considered part of the match. If you had more matching criteria later on, the T would participate in that matching criteria. The reason this is called a look ahead is because you're looking for writing, the match looks ahead to see if it's a T. If it does find it, then it matches, but it doesn't use the T as part of the evaluation. Here's another example. This is looking for 4 digits, and then followed in a look-ahead group by the literal left square bracket, a /w, and the literal right square bracket. This matches the model numbers below. Because it's a look-ahead, only the 3990 actually participates in the match. But you'll notice because the look-ahead is there, none of the other 4-digit numbers is matched. The look-ahead looks for the square bracket, letter, square bracket form, limiting this to just the digits inside of the model number. Changing the equals sign to an exclamation mark changes it to a negative look-ahead, meaning only match situations where the digits are not followed by square bracket, letter, square bracket. This matches all the 4-digit numbers that aren't associated with the model number. Question mark less than equal is look behind. This is a similar concept to look ahead, but it happens before the pattern that you're looking for. So in this situation, I'm looking to match the literal left square bracket /w literal right square bracket preceded by 4 digits. Notice that I was explicit about how many digits was here. Due to the way regular expressions are implemented, look behinds have to be of a fixed length. If I change the /d curly bracket 4 to be /d plus, it will fail. Regular expressions are built on something called finite state machines. Finite state machines only allow certain kinds of computing patterns, and this is not one of them. In the reference material in a later lesson, I'll show you where you can dig out more information on how this works. You can also negate look behind. Question mark less than exclamation mark is a negative look behind. This is looking for 2 digits not preceded by 2 digits. And finally, every good programmer knows to put comments in their code. You can put comments inside of your regular expression. Question mark hash is the comment symbol. Anything inside of the group is ignored. This is part of the regular expression standard. In Python, where you have the verbose flag, I would much rather use that. It's far clearer than trying to insert this inside of your regex. Next up, I'll show you some fun regular expressions. And by fun, I mean horrific. In the previous lesson, I showed you how to up your pattern matching game with conditionals and look-aheads and look-behinds. In this lesson, I'll show you some fun regular expressions and point you at some further reading. There's a famous quote that's been kicking around the internet for quite some time. Some people, when confronted with a problem, think, I know, I'll use regular expressions. Now, they have two problems. This was originally attributed to Jamie Zawinski, an early Netscape engineer, and the example I'm going to show you now is probably why he said it. In the first lesson, I showed you this horror show. This is a regular expression in a Perl module that validates the headers like to and from inside of a mail message. Although it's long and complicated, you do have the capability now of understanding what's in it, if you have a few hours to spare and want to break it down by pieces. Generally speaking, people don't write regexes like this. They're very hard to debug. So where did this come from? Here's the Perl code that actually generated it. Still not easy to understand, but a little easier. If you want to dig through it, start at the bottom. Look at what's being returned. The address variable consists of the mailbox or the group variables. The mailbox and group variables are based on address specs and phrases, etc., working its way up to the top until you have the entire regex. Regexes being what they are, there's an entire sport on the internet to coming up with obscure ones. Here's the first portion of one that determines whether or not a string of numbers is divisible by 7. Code golf is the practice of finding the shortest possible snippet to solve a problem. Regex code golf is a subset of this based on regular expressions. The first part of that divide by 7 regex that I showed you is actually over 25,000 characters long. Stack Exchange hosts a code golf section. This question was posted and people tried to top it. One enterprising individual actually got it down to only 103 bytes. Now they had to use a .NET specific version of the library, and that's because the .NET library supports recursion inside of regular expressions. By creating a recursive regex, the number of bytes in the regex was drastically reduced. Of course, I'm not suggesting you use a regex to decide whether or not something's divisible by 7. There are far easier ways of doing it. Speaking of taking the hard route, here's a function that uses a regex to show whether or not a number in a string is prime. It's not particularly efficient, but it is clever. This regular expression requires the number to be expressed in unary format. Unary format is just the number 1 repeated for the length of the value you're looking for. So 4 is 1111, or length of the string is equal to the value of the number. IsPrime takes n, and the right-hand side of the re.match function call multiplies 1 by n, i.e. repeats it n times, converting an integer into a unary format. Left of the pipe is $$? This matches a single digit 0 or 1 times. So if the string consists of a single 1, it will return true. Because of the caret and the dollar, it can only consist of that single 1. If that evaluates to false, then the right-hand side of the OR gets evaluated. The right-hand side of the OR consists of an anchored expression. This is the full expression using the caret and the dollar sign. If you were using Python 3.5 or greater, you could use the full match function instead. Inside of the group, it's looking for a character, and then a character repeating 1 or more times in the non-greedy format. Outside of the group is a back reference. So this first tries to match 2 characters, then 3 characters, etc. The back reference will look for duplicates. So if you have 2 characters and then 2 characters, that means it isn't prime, because you've got 2 and then 2, which isn't prime. It does the same for 3 and 3, 4 and 4, etc., running all the way up. This is essentially the equivalent of taking your number, dividing it by 2. If you get a whole number, it wasn't prime. Taking your number, dividing by 3, and doing that all the way up to the length of the number. As I said, not particularly efficient. This clever little trick is from a Perl hacker known as Abigail. If you want to see more details about how this works, and particularly how it works in different languages, Ilya has a great article available here that tears it down. Xavier Noria has made a whole repo available with regex patterns for math. You've seen me using Pythex to demonstrate and debug my regular expressions. Another useful site is Regex 101. I find Pythex a little easier to use, it isn't as cluttered, but Regex has an interesting feature that it will break down exactly how the regular expression works and explain it to you. If you're struggling to debug a pattern, watching how it's broken down may help you find your problem. There's a third-party regex library available on PyPI. This one includes nested sets, set operations, and infinite look-behind. It's far more powerful than what's built into Python's standard library. Another alternative for you to look at is the Parse Library. Parse doesn't actually use regular expressions, but solves many of the same problems, and tends to be easier to read than regexes are. If you're doing a lot of text matching, you may find this library helpful. As always, Wikipedia is an invaluable resource. Here's an article on regular expressions themselves, as well as specifics to Perl-compatible regular expressions. As I mentioned in the previous lesson, regexes are built on finite state machines. There's a whole school of computer science based on these ideas. You can read more about them here. And finally, you need to be careful with how you use your regular expressions when they're publicly available. There are ways of creating text that will cause your regular expressions either to hang or become computationally expensive. This is called a regular expression denial of service attack. This article here will give you more information on how to protect yourself from it and what kind of regexes are vulnerable. I'm sure you're ready to do mathematical proofs in regex now, but before you do, continue on to the summary and I'll wrap things up. Thanks for sticking with me so far. I'm just going to wrap things up with a quick review. In the first lesson, I covered what a regular expression was, where they came from, and why to use them. The first regex you were taught was plain matching, just looking for straight characters like SPAM inside of a sentence. Class matching gives you the ability to match a range of values. In this case, the numbers 0 through 9 are in a class. This matches the 2 in second in the sentence. Metacharacters are often used as shortcuts for certain kinds of classes of characters. \s is whitespace, \d is a digit, and \w is a word character, a letter, a number, or an underscore. This comes from what is a word or a valid variable name in programming languages. This is matching the space, the 2, the n, and the d inside of this sentence. Anchors give you the ability to control where in the text a match happens. The caret anchor on its own looks for things at the beginning of the string. Applying the multi-line flag changes this to be not just the beginning of the string, but also after new lines. This example is finding the my after the new line in the middle part of this string. Quantifiers give you the ability to repeat things. \d means a digit, and plus means one or more matches. Search returns the first match for this, which is the 555 portion of the phone number. It's a little suspicious. Using parentheses, you can group values together. Things that have been grouped can also be pulled out using the groups function. Python provides 5 mechanisms for straight pattern matching. Search looks for the regular expression inside of a string. Match looks for the regular expression at the beginning of the string. Full match looks for the regular expression matching the entire string. Find all returns a list of matches, and find iterer returns an iterator of matches. The first 3, search, match, and full match, return match objects. Find all and find iter do not. The match object returned from one of those functions has methods on it. 3 of those methods allow you to get any grouped patterns. Group takes an argument and can return one or more of the grouped patterns. Groups returns a tuple of all of the grouped patterns. Group Dict returns a dictionary for any of the named groups. Expand can be used to turn back references into their actual values inside of a template. And then start, end, and span give information about where the match happened inside of the string. The start and end being the beginning and end of the matches, and the span being a tuple containing the start and end value. You can also use the index of a match to access the group of that number. In the example below, the first group is found using match square bracket 1. Remember that group 0, and therefore index 0, is the entire match, whereas 1 and higher are the numbered back references. If you don't like using a number for the group, the question mark capital P operator allows you to name it. What appears inside of the angle brackets is the name you give it, and after the angle brackets, the regular expression for the group. In this example, there are two named groups, one called prefix and the other called line no. Group Dict function on the match object returns these two groups with their names. Back references refer to a group earlier in the regex. You can specify a back reference with a number, or if the group was named, with its name. \1 is the first group. Question mark capital P equals says to use the group named. In the example here, the group name is twice, and the back reference twice is referenced afterwards. Back references are often used for looking for repetition, as in both of the examples here, looking for the numbers 4, 4 repeating themselves. The RE module provides functions for doing substitution. Sub and sub-n substitute based on regular expressions and values or on a function that you can pass in. Sub-n does exactly what sub does, but instead of returning the substituted string, it returns a tuple containing the substituted string and the number of characters that were substituted. Split is a more advanced version of the string split, allowing you to split based on regular expression pattern matching. Escape is useful for turning a string that you want to find literally that possibly contains special regex characters. Running escape on the string returns an escaped string, which will safely look for a literal version of what you passed in. Most of the regular expression functions support flags to modify their behavior. The example here changes the search to be case insensitive. Small a is found even though capital A was in the regex. There are flags for ignoring case, changing the behavior of anchors in multiline, changing the behavior of a period to include new lines, verbose for making your regular expressions easier to read, debug for showing information about how the regular expression is operating, and the ASCII Unicode and locale flags for changing the style of character encoding used inside of the regex. In Python 3, the default is Unicode. I also showed you how to do conditional matching, changing the criteria based on the presence or absence of a group. I followed that up with look ahead and look behind matches, which allow you to look for things that are preceded or followed by something, but that something isn't consumed. Regular expressions are a powerful tool in your tool belt. I hope you've enjoyed the course. I know I've enjoyed giving it. Thanks for your attention.